Welcome to Volume of a Random Leaf Complement. Before I start, I would like to thank the organizers, Martin Bock, Siddhi Krishna, and Alison Miller, for organizing this Nearly Carbon Neutral Geometric Topology Conference 2021, and also thank Tommaso Cremaschi and Andrew Yarmola, the organizers of this special section on hyperbolic manifolds, for inviting me and giving me the opportunity to give a talk in this section. What I'm going to be talking about today is joint work with Yannick Krivka, Tommaso Cremaschi, and Franco Vargas Payete, and it's work in progress. And I'm going to be presenting one of the main results of that project. I'm going to be talking about volumes of a specific type of three manifolds. These three manifolds are called leaf complements. And I'm going to be looking at a specific type, very special type of such leaf complement called random. Okay, so this talk is about volumes of three manifolds. So let's start. So first of all, what is this talk about? Well, we'll start by looking at the unit tangent bundle. So X, first of all, is going to be a closed hyperbolic surface. And then the unit tangent bundle, which I will denote by UTX, is a three manifold consisting of the pairs of points, X and the surface, and the unit norm vectors, V sub X, based at the point X. And I'm going to be calling this pair of data point together with a unit vector based at that point by the simplified notation, just V. Okay, so V is going to be a point in the unit tangent bundle. A cartoon, if you wish, of the unit tangent bundle could look something like this. I'm drawing this, if you see here, this blue kind of three-dimensional box to indicate that this is a three-dimensional object. And then I'm drawing these trajectories. You can see there's a green trajectory, and you can see there's red trajectories. You can imagine these trajectories as a foliation induced by the leaves of the geodesic flow. So if you give me one point on the surface together with a unit vector, there is a geodesic, unique geodesic, going through that point at that on that direction, and I can follow that geodesic for some time t, and that induces what is known as the geodesic flow, which will be introduced some slides later on in this talk. The trajectories of this flow foliate this three manifold, and they give you this decomposition of this three manifold into one-dimensional trajectories. Some of them are dense, and in fact they never close up. Some others are periodic, and they look like this green trajectory here, which closes up. Given a closed geodesic on the surface X, we can define a lift of this geodesic to the unit tangent bundle. That's called the canonical lift. Well, to specify a lift, I need to the unit tangent bundle, I need to specify both a point on the surface together with a direction. And there's a natural direction to choose. If you have a geodesic, you can look at the derivative of the parametrization. And if you want to pick a unit vector, you can normalize by dividing by the norm of that derivative. So that's what I do. This is the canonical lift. The canonical lift is a choice of a point on the curve together with its unit tangent vector. So such a geodesic induces this canonical lift in the unit tangent bundle, and this canonical lift is actually a knot inside of this three manifold, which is the unit tangent bundle. And whenever you have a three manifold, such as the unit tangent bundle, and a knot inside of that three manifold, such as the canonical lift of a geodesic, you can do an operation that's called drilling. So what does it mean? So you have a knot inside of a three manifold, a knot K inside of a three manifold M. Drilling the knot K from this three manifold M means the following. You take a tubular neighborhood of radius epsilon of this knot K. So here in this picture, again, we go back to the picture of the unit tangent bundle that I showed you in the beginning. And you can imagine that this knot that we constructed corresponds to one of these periodic trajectories of the geodesic flow. So that's the canonical lift of gamma, this green trajectory. And then what I did is I took a small tubular neighborhood of this trajectory, and then I'm going to remove that. So I'm going to take the complement of the unit tangent bundle, or this three manifold in general, M minus that tubular neighborhood. That gives me a new three manifold with boundary, the boundary coming from this. Essentially, the boundary is going to be a torus boundary coming from this tubular neighborhood that I removed. And again, if I specialize to the case of the three manifold being the unit tangent bundle and the knot in question being the canonical lift of some closed geodesic gamma, I'm going to call the three manifold, the resulting three manifold obtained by drilling, the canonical lift complement. And I'm going to be denoting it by M sub gamma. Okay? So in this notation, I'm kind of hiding the fact that this I'm not dealing with gamma anymore. I'm dealing with its canonical lift. There is a theorem by Fullen and Hasselblad from 2013 that says the following. If gamma is a curve or a geodesic on a hyperbolic surface X, which is satisfying the following three properties. First, it's filling. Filling means that any other geodesic on the surface, whether if it's closed or not, intersects this curve non-trivially, or in other words, if you cut the surface along this curve, you obtain a union of closed disks. That's what filling means. These are two possible equivalent definitions of filling. The second property is that the curve should be primitive, meaning the curve gamma can be a power, a non-trivial power. So in other words, you can have that our curve gamma is some curve eta to some power n. That can happen. And then the third condition is that it's in minimal position. If you're working with closed geodesics, that will always be satisfied. But in general, this statement is more allows for more general curves that need not be geodesics, as long as they are also in minimal position. Given these three conditions, Fullen and Hasselblad prove that this three manifold that you can obtain by drilling, that we call M gamma, this canonical lift complement, is a hyperbolic three manifold. So it's hyperbolic. So among the possible geometries that you can give to a three manifold, that this particular three manifold can be equipped with a hyperbolic geometry. So a very interesting result, a very interesting way to produce hyperbolic manifolds. Let's talk about some properties of this canonical lift complement. So the first property that I write here as a proposition by citing some work of Rodriguez Migueles in 2020 is that the homeomorphism type of the canonical lift complement does not depend on the choice of the hyperbolic structure that you picked on your surface. So if you happen to pick a different one, you will get a different canonical lift complement, but it will be homeomorphic to the first one. And also another important property is that if you have two curves that are in the same mapping class group orbit, meaning that they're of the same homeomorphism type, then their corresponding canonical lift complements are homeomorphic. Okay, these two results follow from topology of surfaces. In particular, this one here follows from the fact that if you have two curves on a surface that have the same minimal self-intersection number, then you can construct a homeomorphism between the complements of these curves on the surface. So these are two very interesting properties. Moreover, because of most of rigidity, in fact, not only these canonical lift complements of curves in the same mapping class group orbit are homeomorphic, but in fact they are isometric as three manifolds, because if two hyperbolic three manifolds are homeomorphic, then it follows that they are also isometric by most of rigidity. And therefore, if I can look at their volume, their hyperbolic volume, and this volume will be a mapping class group invariant geometric quantity. And so that's one of the geometric quantities I'm going to be looking at, the volume of these three manifolds. So there's another natural geometric quantity here, which is the hyperbolic length of gamma, right? So I started with a curve with a closed geodesic gamma. It makes sense to consider its hyperbolic length on the surface. And then from gamma, I constructed this other object, this three manifold, by taking the canonical lift of gamma to the unitangent bundle and drilling it from the unitangent bundle and obtaining a hyperbolic three manifold. And I'm looking now at its hyperbolic volume. So I would like to compare this length with this volume. Let me give you a couple of examples of families to see what kind of behaviors you can expect. So here we'll be comparing hyperbolic length and volume. So take a filling closed geodesic on the surface and take a mapping class of infinite order. I mean, the typical example is look at this fourth punctured sphere, for example, and take this curve that goes around two of the punctures, and then take a half twist, right, that switches these two. And so you obtain this new curve, and then keep doing the same operation. So apply this half twist again. By applying this infinite order map twice, you get this more convoluted curve. You can keep applying this more and more times, and you see you keep getting this longer and longer curve. This picture is borrowed from Bonahon's notes on foliations. But in general, what you can see is that the length of p to the n of gamma goes to infinity, whereas the volume of the corresponding canonical leaf complement stays bounded. Because, as we've seen, of course, phi of n is in the mapping class group orbit. So phi of n gamma is in the mapping class group orbit of gamma. So their volumes have to be the same. So that's an example where the length goes to infinity and the volume stays bounded. It's a little bit boring, right? Because not only we know that the volumes are the same, but also we know that all these canonical leaf complements are actually isometric as surfaces, as three manifolds. So slightly more interesting example was constructed by Rodriguez-Migueles, where he constructed explicitly a family of filling curves, gamma n, that were pairwise non-homeomorphic, and for which their volumes were also bound. Okay, and he actually does this construction explicitly. So here's a picture I borrowed from his paper, and in the same project, in the same work by Rodriguez-Migueles, and also in later work, he actually constructed explicit families of filling curves for which he can give a lower bound, which is sublinear as a function of the hyperbolic length for their volume. So what he can show is that for some constant that depends on the hyperbolic structure x, he can construct a family of filling curves whose hyperbolic length, for which you can give a lower bound in terms of some sublinear function f for its hyperbolic volume. And this sublinear function is the following. It looks like this. So it's a sublinear function that's essentially t over w of t up to some constants, a and b. Here, w of t is the Lambert function. Okay, so it's a function that's essentially, when you look at its asymptotics, when t goes to infinity, the asymptotics, it behaves like at first order like logarithm of t, and then at second order as logarithm of t. Okay, so essentially, you can think of this as a function of t over logarithm logarithm of t minus logarithm of t at to first order. So Rodriguez-Migueles constructs these examples that grow like that. And these are pretty much the best lower bounds to the moment, in the sense that they grow as fast as we know. We don't know any other families of affiliate geodesics that grow at least at this rate. The other thing that we know is that Duke, William Duke, in his paper Hyperbolic Distribution Problems and How the Integral Weight Mass Forms from 1990, he constructs families of equidistributed affiliate geodesics on the molar surface, and Brand, Spinsky, and Silverman compute numerically the lengths, the geodesic hyperbolic lengths of these curves, and compare them to the corresponding volume of the canonical leaf complement. And numerically, what they obtain is a graph like this, which, well, it looks maybe linear or maybe sublinear. It's not clear, but that's some numerical evidence that should suggest that it should maybe grow like a linear or like a sublinear function that's very close to being linear. So this is what we know. And then let me also introduce another result that is going to play a very important role in this talk, which is the combinatorial lower bound on the volume given by Rodriguez-Migueles. So to introduce this lower bound, I need to introduce the notion of gamma arc. So if you have curve gamma, geodesic gamma, or curve in minimal position, and you have a pair of bands, or a pair of bands in composition P, a gamma arc is the intersection of the curve gamma with one of the pair of bands of this Penzic composition. So for example, here's this red curve here is gamma, and we have a pair of Penzic composition for this genus 2 surface consisting of two pair of bands. And here's one pair of bands, let's say P1, and here's the other pair of bands, let's say P2. This curve gamma intersects one of the gamma arcs of this curve gamma would be this blue gamma arc that goes from this boundary component of this pair of bands P1 to this other boundary component of this pair of bands P1. That's what a gamma arc is. And we will consider gamma arcs, or in general arcs in a pair of bands, free with respect to free homotopies relative to the boundary, meaning that the endpoints in the boundary can be are free to glide. So if you, for example, have the following curve that goes from this boundary to this boundary, this dark blue curve is actually freely homotopic to this other light blue curve, because I can glide this end of this light blue curve homotopy and twist this component and bring it to the dark blue one. And having said these two things, I can introduce Rodriguez-Migueles lower bound. So given a pair of Penzic composition of a closed parabolic surface and a filling closed geodesic, Rodriguez-Migueles gives a lower bound in terms of the number of free homotopy classes of gamma arcs in each pair of bands of this Penzic composition. So you can count the different numbers of free homotopy classes of gamma arcs in P, and then sum over all the pairs of bands, multiply by some constant, V3, which depends on, which is essentially the volume of the regular ideal tetrahedra, and this gives you a lower bound for the volume of this canonical leaf complex. And this is essentially the only lower bound that's known. It's a combinatorial lower bound in nature. So if you want to obtain it, you need to study, you need to count curves or arcs on pairs of bands. And in general, we don't know any geometric lower bound at this point. So this will be one of the main ingredients that we'll use in the proof of our main theorem that will I will state closer to the end of this first part of the talk. So let me now start. So at this point, I've introduced all the results that were either known or that we will be using also. And now I will start with some material that we will need to state our main result. So in our model, we want to define a random canonical leaf conflict. And so this is going to come from a choice of a random, closed random geodesic. There are many ways to produce a closed random geodesic. Here's one way to do it. So what we will do is we will construct a model of a closed random geodesic, and we will use this combinatorial lower bound that was given by Rodriguez-Migueles to give a lower bound to the volume of this random, of the corresponding canonical leaf for this closed random geodesic. So again, let me remind you the geodesic flow, right, is defined as follows. You pick a point in the unit tangent bundle and flow along the corresponding geodesic for time t. Here it will be denoted by G sub t. The geodesic flow is topologically mixing. It means the following. So if you have two open subsets of the unit tangent bundle, then you can find some long time t, so that for all t larger than that long time t, the intersection of any of these two open sets, so this time t will depend on these two open sets, but you know there exists such time t, so that for all large time t, b, the intersection of b with the flow, the translate by the flow of this open subset A is non-empty. Okay, so if you have two, in principle, completely disjoint open sets, and you fix one of them, and you let one of them flow and follow how it flows along the by following the geodesic flow for a very long time t, eventually the geodesic flow is going to make it intersect with your fixed open set B. Okay, and so one way to think about this is that in the long run, the geodesic flow diffuses things so much that even if you start with two completely isolated open sets from each other, eventually the geodesic flow will diffuse things in such a way that they will end up intersecting. And so using this as one of the ingredients, we'll build this random closed geodesic. So here's how we will build it. Pick a point at random with respect to the you will measure, so the volume measure on the unit tangent bundle, and flow along the geodesic flow for a very long time. And then by mixing, you know that if you pick a very small ball around V, eventually we'll come back to that small ball. This means that you will come back to a point V that's very close, both in this point to the point on the surface and also in its direction. Now, because of topological mixing, you can actually guarantee that when you come back to this original point, and if you close off by an almost geodesic path, the resulting curve that you get, even though it's not geodesic, it's not too far from being a geodesic in a very precise sense. And an important property about this, so that's our model for a closed random geodesic. So we follow the geodesic flow for a long time, and then we close off by this short arc. And then Birka-Vigotti theorem tells us that if you look at the flow for almost every point in the unit tangent bundle, if you look at the corresponding geodesic trajectory of the geodesic flow, and if you look at its at the time average of this geodesic flow trajectory, it actually ends up converging to the space average, okay? Which in terms of curves, it translates to the fact that this random closed geodesic that we constructed, if you divide it by its hyperbolic length, it converges in the sense of geodesic currents, to the Liouville current. Okay, the Liouville current is a current that comes from the Liouville measure in the unitangent bundle. And one important property of this Liouville current is that it's filling as a current. And because of that, and some other considerations, one can show that for t long enough, this closed random geodesic that we constructed is actually filling, which is one of the hypotheses that we will need to use to apply full-on Hasselblad's theorem, right? One of the conditions was that the geodesic that we start with should be filling in order to get a parabolic manifold. So here's the statement of the main theorem, and with this I will end this first part of the talk. So what we show is that if you start with a closed hyperbolic surface and a pair of points decomposition, P, and if you pick the primitive element of a random closed geodesic, so the random closed geodesic that we constructed need not be primitive in principle. In fact, in general, you can have such constructions of random closed geodesics that give you non-primitive curves. But we can always take its primitive elements. So if our curve gamma b of t is non-primitive, then we know that there is it's a power of some primitive curve, and we can always take this primitive curve. So what we can show is that there are constants a and delta between 0 and 1, and b positive that depend on the hyperbolic structure X and its this pair of points decomposition that we picked, so that we can obtain a sublinear lower bound that depends on this function f of t, which is the same function I gave you before. There was t over the Lambert function of t. There's a slight difference, though. Notice that we have to raise that sublinear function f of t to this power. This power is has an exponent delta over 2. Here, delta is between 0 and 1. In fact, by choosing the pair of points decomposition wisely, we can always make delta as close to 1 as we want. So we can always make this exponent as close to 1/2 as we want. So this lower bound is not quite as good as the lower bound that Rodriguez-Migueles finds for his families of explicitly constructed families of geodesics. However, our closed random geodesics, we know that they're equidistributed in the unitangent bundle. So they behave similarly to the examples provided by William Duke in his 1919 paper. So that's a statement. That's a theorem that we prove. So that this random canonical leaf complement, the volume of it, is lower bounded by a sublinear function in terms of the length of this random geodesic. So here again, t is proportional to the length of the random closed geodesic because of the way we construct the random closed geodesic, right? So I will stop here, and then in the next part, the second part of the talk, I will say a few things about the proof of the statement.